So last time we introduced work, and now we're going to tie it to energy. So to this lesson's work and kinetic energy. And kinetic energy is the energy of motion. This is energy of motion. This is energy of motion. Okay, so when things are moving, they have some energy. We call that kinetic energy. Kinetic means to move. Okay, so to get to this, there's a derivation in the book, but I'm going to walk through it as well. And we're going to start, I'm going to do it a little differently though. We're going to start from Newton's second law. So the acceleration of an object is equal to the net force divided by the mass. And what we're going to do is we're just going to simplify it and just say that, you know, we have an object, has a force applied, and then we have some acceleration. So just a single force, and we're just accelerating linearly. So I'll rearrange this. So we get the force in the x direction is going to be the mass times the acceleration. Okay, so we want to, instead of thinking about acceleration, we want to talk about a change in velocity. So we're going to go over to kinematics real quick and get some expression for acceleration that we can use. And we're going to use this one. So our Vf squared is equal to V naught squared plus 2a times x minus x naught. So we're using this kinematic equation, and what I'm going to do is solve for a so that I can plug it back in here. So we'll move this over. So we get Vf squared minus V naught squared is equal to 2a. And instead of x minus x naught, I'm just going to put delta x. It's a little easier. And so we see that we get Vf squared minus V naught squared over 2 times delta x is equal to a. So now we'll take this and we're going to plug it in here into Newton's second. So over here we'll get force is going to be equal to mass times all of that. So times Vf squared minus V naught squared over 2 delta x. All right, now let's distribute and then we'll move some stuff around. So we get force is equal to distribute the mass. So we get mass Vf squared minus mass V naught squared over 2 times delta x. And then what I'm going to do is I'm going to move this delta x. So we'll multiply it up here. So we get force times delta x, or displacement. And this 2, I'm going to write it out here in the front. So that's like 1 over 2. 1 over 2 times all this stuff inside. mvf squared minus mv naught squared. So all I did was pull out the 2 out in front and move the x over. Okay, so now we're about done. I just have to distribute. So we get 1/2 mvf squared minus 1/2 mv naught squared. So we have a couple things here. One, force times displacement. Oh, that's work. And so then we have equal to. So then we have the same quantity. So we have this final velocity squared and the initial velocity squared and then half the mass. This is called kinetic energy. And so we'll define kinetic energy to be 1/2 mv squared. So if I know the mass and velocity, that's how much energy it has. And so what we have here, if I change this, work is going to be my final kinetic energy minus my initial. Yeah, so this is the Work-Energy Theorem. We're going to generalize it because we can actually do this with all energy that's involved. But for now, we're just thinking about things that are moving and the amount of energy that is stored. Notice that the units are the same. So this is energy, and this is work. So this is all in joules. So we're talking joules here, here, and here. Everything's in joules. Okay, so let's apply it. So first let's just do some straight up kinetic energy problems. So let's think if I have a mass moving at some velocity. What I want to find a new kinetic energy if I have 3 times the mass and let's say 5 times the velocity. What's the new kinetic energy? So let's find our original kinetic energy. Our kinetic energy in this case would be just 1/2, and then its mass is m v squared. So that's our original. I'll put a little O. And then we have some new kinetic energy. So the new kinetic energy would be 1/2 of 3m times 5 times the velocity squared. So now we're just gonna, like we've done before, I just want to pull all the numbers out front. So I get 1/2, this is 3m, and then inside is 5 squared, so that's 25v. So 25 times 3 is 75. So I get 75 times 1/2 mv squared. I forgot to carry that square. So what you can see is my new kinetic energy is 75 times the original one if I just have 3 times the mass and 5 times the velocity. So those are just straightforward, just calculating the kinetic energy of a moving object. Let's think of it. How about this one? Let's drop an object. So say I had an object of mass, I don't know, let's say 3 kilograms. And so I drop this thing and I let it fall for a certain distance. We'll say 10 meters. How fast is it going? So what you may be tempted to do is use some kinematics or dynamics or something, but energy makes this so easy. You're gonna like it. So I'm gonna use energy. So work is change in kinetic energy. And work, we learned, is just force times distance. And my change in kinetic energy would be my kinetic energy final minus initial. Do you notice this feels like momentum? I hope you start realizing that. Like the form is similar. We did force times time and change in momentum. Now we're just doing change in energy, and we use distance instead. Okay, so the force acting on this ball is just the force of gravity times delta x. And my initial kinetic energy, well, this thing's not moving to begin with. We just dropped it, so there's no initial kinetic, so we just get that. So it's 1/2 mv squared. Now I just solve for v. So we multiply 2 over. The force of gravity is m times g delta x. And then equals, so I move the 2, so we get mv squared. Then you see the mass cancels, and I take the square root. So it's square root of 2g delta x. Hey, this looks familiar. I think we've gotten this out of kinematics, haven't we? Yes, we have. Because if I did the kinematics, my final velocity squared would be the initial squared plus 2a times delta. I put delta x, but it's delta y. Anyway, delta x. And you can see that's going to be my 2g. There's no initial velocity. And so I get Vf is the root of 2g delta x. So it's the same. Anyway, energy is quick. It doesn't matter what you do with the, well, in this case, you'd have to flip and say that the velocity was negative, but you'll never have negative kinetic energy because we square the velocity. That's important to know. So what would this be? Well, it would be 2 times 3 is 6 times 10 is 60. So root 60 is the velocity, but then it would be negative because it's down. All right, so I'm trying to think of another one. Let's say you have something that's moving, so it has a velocity of 2 meters per second, and then after some time period, or some distance rather, we don't even care. Let's say it has a velocity of 5 meters per second. How much work was done? Okay, so work again is change in kinetic energy. So we would get the the kinetic energy final minus kinetic energy initial. So that's 1/2 m vf squared. Don't forget these squares. That's where you're going to mess up, especially after working with momentum. Be not squared. So I can factor out the 1/2 m, and it's going to be vf squared. So 5 squared minus 2 squared. So you get 1/2 of the mass times 25 minus 4 is 21. And then mass, I don't know, whatever you get. Mass is 3. So that's ugly. Let's do 4. Okay, half of 4 is 2 times 21 is 42. So 40 joules of energy were put into the system through work. But that's basically it for examples. There is one other thing that I wanted to show you, and so that has to do with what work is, our definition, and that's force times displacement. So this is going to come up on graphs. So if I have if I plot force versus position, then I could get a graph that, say, I don't know, let's say like this. And then it drops down, and then I apply a force, and then it's gone. Okay, so let's say that this is 2 and then 1.5. And then we'll do 1, 2, 3, 4. And these are going to feel weird whenever you see them, especially after we haven't done this for a while. But if the initial velocity is 0, the mass, let's say 2 kilograms, what's the final velocity? And you're gonna look at this thing and be like, what? There's no way. So force, pay attention to what we're looking at. It's force and distance. So that gives me work. And so force, remember, work is force times distance. And whenever I have a multiply, that's area. So if I have force plotted versus distance, I can get the area, and that's going to tell me work. And then work is change in kinetic energy. So we get kinetic energy final minus initial. And there was no initial velocity, so there's no kinetic energy. So the work in this case is going to be all kinetic energy, 1/2 mv squared. So let's figure out what the work is. So again, it's the area on a force versus position graph because we're multiplying. And so what I'm looking at is I'm going to look at the area here and then the area here. And we'll just get the total. These are above, so it's positive. Remember, if it's down below, that's negative. And so this, you can see, is a rectangle. It's a 2 by 2. So the work done here is 2 times 2. We get 4 joules of work. And then we come over here, and this is 1.5. But the length is not 4, it's 2, because it's 2 to 4, so times 2. So the work here is going to be 2 times 1.5, which is 3 joules. So the total work is 7 joules. So we got 7 joules of energy put in. So let's go over here. It's so crazy how easy these become. I know it doesn't seem like it right now, but 1/2 of the mass, so 2 times the v squared, those cancel, so it's square root of 7. That's the velocity. Done. So anyway, remember that. The work is going to be the area on a force versus position graph.